I do want to share some, motivation behind this, this talk first. So I would say as a rookie in our field, I always have a hard time, finding a good topic, not just a doable topic, but an extensible topic, So every time I don't have any idea, I just go to like Chris' website or Margin's website and try to, get some idea out of that. And this topic is exactly motivated by, by Chris' work back to 1990s with some of his co-authors. So let me begin this talk with some, notations and definition, because this is about some, Gabor thing, right? So assume that G is, functioning in L2R, and the lambda is a countable subset of R2. Then throughout this talk, I will use this notation G lambda to denote a Gabor system, associated with G and lambda. And I will use, the notation MBNTAM, to denote the modulation, where I define, for any non-zero AB, the modulation MB is defined, by the multiplication by exponential to a 2 pi IBX, and the TA is just the usual translation by A. So this is the notation I'm going to use throughout this talk. And the main idea behind, this talk is that, so how dense, is the distribution of this, set of time frequency shift in R2 if this Gabor system has some, nice approximation properties. And this is actually a very broad idea, very broad question, in the sense that, you can define your own criterion to estimate the density, and you can also define your own nice approximation properties, right? And I'll get to, how I estimate the density, perhaps in 10 minutes. But let me get to, the part how I define my own nice approximation properties. So to me, a nice approximation property must be established on the following formula, the so-called reconstruction formula. So we say, a Gabor system satisfies the reconstruction formula if, if every x in L2R can be written as the summation of, some coefficient and times, MBN times TANG, and with the convergence of the series in the norm of, this should be L2R. But, this is, far from being a good approximation property, right? Because at first, we don't even have any control over the coefficients. So is it possible that we can find some, some sequence of coefficient functionals, let's say Yn, such that, every Cn here can be realized as the inner product of x and Yn for all x in L2R. And sometimes the convergence of the summation on the right-hand side of this equality, might subject to the order of the summation. That means that if, you have to follow certain, certain enumeration of your sequence, otherwise you may end up with divergence. So that is it possible that we can, get some, unconditional convergence of the series, in this formula? And also, under what circumstance, can we have the uniqueness of the series representation on the right-hand side of this, infinite series? So as long as, a Gabor system not only satisfy this reconstruction formula, but also one of these three properties, then I say it has a nice approximation property. So now I can, reformulate my question, and make it more precise. But before that, let me give a names, to those Gabor systems which satisfy at least one of these, three properties. So the first one is, we say a Gabor system is a Schauder frame for L2R if there exists some sequence Yn, which is usually called the coefficient functional, such that, every element x can be written as, this series representation. And of course, with the convergence of the series in the norm of L2R. So now for Schauder frame, we at least have some, control over the coefficients. And next, we want, as I mentioned, the second nice property, the unconditional convergence, right? So we say a Gabor system is an unconditional Schauder frame if, it is a Schauder frame, but also it has, unconditional convergence for the, series representation on the right-hand side of this equation. And if a Gabor system satisfies all, three properties, control over coefficients, unconditional convergence, and the uniqueness of the representation, then we say it is a Ricci basis for L2R. And the frame we are familiar with is kind of somewhere between, unconditional Schauder frame and the Ricci basis. So, the frame we are familiar with is a system that satisfies, the following, frame inequality for all x in L2R. And the one reason I like to, talk about these four notions together is because, there exists some sort of hierarchical structure in terms of inclusion relationship between them. So that is, Ricci basis is part of frames, and the frames is part of, unconditional Schauder frames, and unconditional Schauder frames is part of, Schauder frames. So now, let me make my, original question a little more precise. So how dense is the distribution of the set of time frequency shift in R2 if, let's say, your Gabor system belongs to one of these four families? So Chris and his co-author already made some, contribution to, Ricci basis and the frames, along this direction, and I will mention those results in a second. But still, I haven't specified what my criterion is, for a density criterion, right? So now let me get to that point and show you what my density criterion is. So the density criterion I'm going to use here is still the classic, building density notion. So the lower building density and the upper building density of a countable subset in R2 is defined by, by these two limits, and where this notation QHX denotes, the square center at X with side length H. So let me give you, a visualization, what's going on with these, two limits first. So it's like, you fix your, side length and form a square and try to see how much points of lambda contained in this square, and then compute, the average. And you find where you get the maximum average and where you find the minimum, average. And then you take limit sup and the limit f. So this leads us to the, formulation of upper building density and the lower building density. So this is the criterion I'm going to use to estimate how dense my, set of time frequency shifts is in R2. So now I can make my, question very precise. So what can we say about, the upper and the lower building density of this set of time frequency shifts in R2 if the Gabor system belongs to one of these four families? So of course, I'm going to start from the very left, the Ricci basis, and then frames, and unconditional Schauder frames, and then Schauder frames. Okay, so back to, I believe, 1999. Christensen, Dan, and Chris, they proved the following result. So that is, if you have a Gabor system which is a Ricci basis, then of course the lower building density has to be equal to the upper building density, which has to be equals to 1. And they also proved that if a Gabor system is a frame for L2R, and by the way, although I only talk about the setting L2R, but you can extend this to L2RD, and even with multiple generators, without too much effort. So what they showed for frame was, if you have a Gabor frame for L2R, then the lower building density has to be at least greater or equals to 1, and the upper building density must be finite. Okay, so now the remaining two questions is, if we have a Gabor system, which is, let's say, an unconditional Schauder frame or a Schauder frame, then what can we say about their density, right? But let me talk about, the case of Schauder frames first. So as far as I know, I don't think the following result is ever stated, explicitly in any paper. But what we know about Schauder frame is that if a Gabor system is a Schauder frame for L2R, then the lower building density, can be as low as 0, and then the upper building density, could be as high as infinity. So let me talk about why it is possible that the upper building density could be infinity for, for Gabor Schauder frame. So let me get back to my definition a little quick. So this is the definition of, of a Schauder frame. So you can imagine, because in a setting of Schauder frame, we have certain, flexibility to add some points into the sequence So you can imagine no matter what points you add into the sequence, you can just set the corresponding coefficient functional to be the zero coefficient functional. So you can add whatever point you like into the system and without breaking this reconstruction formula, right? So that's why the upper Pu-Ting density associated with a Gabor Schauder frame could be as high as infinity. And even if you require all the coefficient functional to be non-zero, you can still construct even unconditional Schauder frame with infinite upper Pu-Ting density. And for the lower Pu-Ting density part, so you can even construct a Gabor system which consists of pure translates, which forms a Schauder frame. And when you only use pure translates in your set of time frequency shifts, of course the lower Pu-Ting density is equal to zero. So that's why it is possible you have oh sorry, go ahead. I think so, because you can add whatever points you like, and you just set the coefficient functional to be zero, so it doesn't matter. It doesn't change the reconstruction formula. You get a point? Okay. Sorry? I mean the upper Pu-Ting density part. I don't know, but that's a good question. Doesn't mind. Yeah, I think so. It should work. Huh? Yeah.
Lower density, zero.
Yep.
Your translates are usually, upper density infinity.
Yeah, that's right. I think it still works. You still can add points into the set and set the coefficient function to be zero. And that should give you the example. Right? Am I right? Makes sense? Okay. So now the remaining part, the missing piece is, okay, what can we say about the density associated with a unconditional Gabor Schauder frame, right? And it turns out, surprisingly, if a Gabor system is an unconditional Schauder frame, the lower Pu-Ting density still has to be greater or equals to 1. So I will show you, what's the motivation behind this lower bound in a second. But before that, let's take a look, how Christensen, Dan, and Chris, they prove their result. So a key tool, I would say a key notion they use in their proof is this, this so-called homogeneous approximation property. So assume that we have a Gabor frame, then let me first define some notation first. So assume that AB is just an arbitrary point in R2 and R is a positive number. Then we define WRAB to be the span of NQTPG, where PQ is just a point contained in the intersection of the square center at AB with side length equals to R and this set lambda. And now we say a Gabor system satisfies the homogeneous approximation property if for each f in L2R and the epsilon greater than 0, there always is just some radius R greater than 0, such that for any AB in R2, the distance between this function and this subspace is less than epsilon. So the way I'd like to visualize this homogeneous approximation property is that now just think of AB is the origin. So for this function f, so let me denote the 0 points. Let me use 0 points to denote this points in the set of time frequency shift associated with this graph system. And let me use the green points to denote the time frequency shifts associated with f. So now think of AB is just the origin. So now there exists some side length R, so that there must be enough points contained in this square, right? So that the distance between f and the subspace generated by this 0 points is small enough, right? But now no matter how you move this point, this green point, and this square, there must be still enough points, enough 0 points contained in this square, so that the distance between MBTAF and the subspace generated by these 0 points is still small enough. So that being said, in some sense, I should say intuitively, that means that if you have a Gabor system which satisfies the homogeneous approximation property, then its set of frequency shifts should be high frequency shifts should be denser enough, right? And even more denser than those Gabor systems which don't satisfy the homogeneous approximation property. And from there, they use this to show that this is right. And the density associated with Gabor system is even greater than the density associated with Gabor spaces. So this is how they obtain, that lower bound, 1. So this, motivates me to think about the following question. So now, if we have a Gabor unconditional Schauder frame, does the Gabor unconditional Schauder frame satisfy this homogeneous approximation property? If it does satisfy this homogeneous approximation property, then I can show, the lower bound has to be 1. And surprisingly, if you have, a Gabor unconditional Schauder frame, it does satisfy the homogeneous approximation property. So this leads us to, to get the lower bound where the lower building density has to be greater or equals to 1. So this is the idea. And to me, this result is very surprising because initially I thought, the reason why the set of high frequency shifts associated with, a Gabor system is so dense is because, the frame inequality. The Gabor system has to satisfy the frame inequality so that its high frequency shifts can be denser enough in R2. But now this result shows us, it is not because of the frame inequality, but just the unconditional convergence of the reconstruction formula that will give you a dense set in R2. Okay, and the next result I want to talk about is, is another application of this density result that Christensen and Dan and Chris met back to 1990s about some partial answers to the Ozon-Zollik conjecture. So Ozon and Zollik, they formulated this conjecture back to 1992, saying that if you take a function g in L2R and and any countable subset lambda n from R, then the sequence of translates g of x minus lambda n can never be a Schauder basis. So here, what I mean by Schauder basis is just those Schauder frames with unique series representation in its reconstruction formula for all x in L2R. And in the same paper where they propose this conjecture, they also prove that, such a sequence of translates can never be a Riesz basis for L2R. And Christensen and Dan and the Chris, they proved that such a sequence is never a frame for L2R. So although I only state the form of Ozon-Zollik conjecture with only single generator, but you can have the same result with finitely many generators. So as long as you use finitely many generators, you cannot get a frame by just using pure translates. And it was confirmed recently by Neil Leff and Slishev that such a system of translates can never be an unconditional Schauder frame for L2R. And as far as I know, this conjecture is still open, and the closest result to a full solution to this conjecture was done by Odell and 3 of his co-authors. What it showed back to 2011 was that if you have a generator G, which is contained in L1R and also in L2R, then no matter what kind of translates you use, such a system can never be a Schauder frame as long as the distance between any two distinct lambda n and the lambda n is greater or equals to some positive number delta. And let me mention that before Odell and his co-author proved this result, Chris and then they also proved that back to 2000, if G, the generator, is in L1R and also in L2R, then whatever translate you use, the corresponding system of translate can never be a Schauder basis for L2R. So that result was once the best result for like 11 years until the result by Odell came out. Okay, so now we have seen a bunch of remarkable results about Ozon-Zollik conjecture. But the funny thing is, none of them really say anything about what kind of closed subspace of L2R don't admit, any friend of translates or even unconditional friend of translates, right? So the question is, what can we say about those subspaces of L2R that does not admit, an unconditional Schauder friend of translates or even, friends of translates, right? So this is the question I'd like to answer. So now, still, the idea, behind the main result I'm going to present along this direction is also motivated by the work of Christensen, Dan, and Chris. So let's take a closer look how Christensen, Dan, and Chris provided the partial solution to the Olsen-Zade conjecture. So once again, what they proved was that no system of translates can be a frame for L2R, right? And the way they proved that was, if you have a Gabor system like this, which forms a frame for L2R, then the lower building density associated with this Gabor system cannot be too low, right? So that means that the distribution of this lambda in R2, cannot be too sparse, right? But the thing is, when you use just pure translate, the lower building density becomes 0. So in this case, it is not possible for a pure translate to be a frame for L2R. But the thing is, when I try to utilize this idea to do something about to do something on subspaces, this method kind of completely breaks down, because you can imagine you can always find a Gabor system with 0 lower building density, which forms a frame for its closed span, right? So in this case, that being said, for a Gabor system to be a frame or even an unconditional Schauder frame, the corresponding set of time frequency shifts need not to be very dense in R2, right? So that's the key issue. But still, we can get some motivation out of this idea. So let me give you a visualization behind this idea. Okay, so assume that the yellow points are just pure translates, and we are going to use that to generate some Gabor system, right? And we want to know whether using pure translates can give me some unconditional Schauder frame for some infinite dimensional closed subspace for L2R. And now the block points are just the time frequency shift associated with a Gabor frame. So now to have a Gabor frame, the distribution of these block points has to be dense enough, right? So that being said, as we moves up, the distance between these block points and the yellow points increases to infinity, right? And also when we move down, the distance between these block points and the yellow points also increases to infinity. So maybe density is not the right criterion, but distance is the right criterion. So that's how we can have some chance to generalize the result to subspace. Maybe use the distance criterion. And it turns out distance criterion is the right criterion. So let me show you the criterion. But before that, let me introduce a terminology first. So we say a function in L2R is well localized in both time and frequency if there exists some psi in the Schwartz functions, and such that this L1 norm is less than infinity. So essentially what this norm says is that phi is in the Feitinger algebra, or I should say phi is in M1R. But I don't want to talk about too much about modulation space. So let me just call phi, it's a function which is well localized in both time and frequency. Okay, so now I'm going to present my distance criterion. So assume that we have an infinite dimensional closed subspace of L2R, and assume that this Gabor system G phi gamma is a real spaces for its closed span, just for its closed span. And this Gabor system G lambda is an unconditional Schauder frame for M. Then in this case, if this generator phi is well localized in both time and frequency, then it turns out there must be some infinite subset lambda prime of lambda, associated with this unconditional Schauder frame, such that the suprema of this distance must be finite. So it might be a bit hard to see, why this is an improvement of, not only Christensen, Dan, and Chris' result, but also an improvement of Near-Left and Tzlizhev's result. Let me give you a quick example. So assume that phi is the, Gaussian function. And in this case, for any non-zero b greater than 0, the closed span of this Gabor system does not admit any unconditional Schauder frame of chance states. We know that when AB is less than or equals to 1, the closed span of this Gabor system is just the L2R, right? But when AB is greater than 1, this is just a proper subspace of L2R. So in this case, it does, extend, some known result about ozone-sided conjecture from L2R to a broader, closed subspaces of L2R. Yep. So this is pretty much about the research part I like to talk about today. So as I said, I'd like to leave some words of thanks to the end of this talk. So I would say it might be very hard for me to use English to express like how appreciative I feel for what Chris has done to me. So what I learned from him is not just about math, but about how to be a good person and how to help people around you and how to make a contribution to your community. And so there's an old saying in Chinese saying that, a day an advisor, a lifetime a father. So to me, he's not just my mentor, my advisor, but also my lifetime mentor and my lifetime friends. So I would say thanks for what you have done to me, and thanks for what you have done to your students, and thanks for what you have done to this community. And I believe birthday is meant for people to make a wish, right? So if no one minds, on behalf of all audience here, I'm making the following wish. Thank you so much.